Infrared spectroscopy is used to characterize organic molecules based on functional group. Since we can't visually observe the atoms and bonds in a molecule, we use indirect techniques to determine which functional groups are present. Infrared light causes molecular vibrations. Certain bonds will absorb at specific wavelengths, which will give us information on the strength of the bond and which functional groups are present. An example of an infrared spectrum is shown here. From this spectrum, we can deduce that this molecule contains at least two types of bonds, CH and C triple bond N. The x-axis is in wave numbers. A wave number is defined as the reciprocal of wavelength. You may recall that energy is equal to Planck's constant times the speed of light c divided by wavelength. Substituting for wavelength, we can also obtain E equals hc times the wave number. A wave number is really just the number of cycles in a wave in cycles of a wave in 1 centimeter. If we wanted to convert from wave numbers to wavelength, in this case microns, the equation is simply wave numbers equals 10,000 divided by microns. The y-axis is the percent transmittance, which is the opposite of absorbance. When reporting peaks in an infrared spectrum, we use a qualitative approach, where S is an intense peak, M is a moderately sized peak, and W is a weak peak. Let's now talk about the theory of IR spectroscopy by considering a spring. If we have a block and a ball connected by a spring in a vacuum, and we were to pull them apart, the spring would stretch. The spring now has a high tension and a high potential energy. If we release both structures, the ball and the block would bounce back and forth until they came to rest. Thus, a restoring force inherent in the spring would bring the ball and block back to an equilibrium state. Likewise, if we pushed the ball and the block together, the spring would compress and the distance between the block and the ball would shorten. Again, the spring at this stage would have a high tension and high potential energy, such that when you release the block and the ball, they would vibrate back and forth until they are at rest. This same analogy can be used for chemical bonds. Instead of a block and a ball connected by a spring, we have two atoms connected by a bond. So what kinds of molecular vibrations are there? Well, if we were to extend our analogy of a spring, we would have a diatomic molecule that upon excitation with infrared light would cause stretching of the bond, and then movement back and forth of each atom. This is called a stretching vibration. In a molecule containing 3 atoms, there are several modes of vibration. Infrared light can cause the bond angle between the atom to decrease and then increase as it reaches back to equilibrium. This is known as a bending vibration. In the same molecule, there are 2 types of stretching vibrations. When both bonds lengthen and shorten at the same time, we call this a symmetric stretching vibration. When one bond shortens and the other lengthens, this is called asymmetric stretching. In a complex molecule, many types of bonds will be undergoing these vibrations, all at different frequencies and intensities. So the spectra can become quite complicated. But there are a few factors that determine where the vibrational frequency will lie. Vibrational frequencies are determined by the type of vibration, the strength of the bond, the masses of the atoms, and by electronegativity. The first factor is the type of vibration. If we were to consider the CH stretch versus the CH2 bend, we see that the stretching vibration occurs at a higher frequency. This tells us that stretching vibrations require more energy than bending vibrations. The strength of the bond, or bond order, also has an impact on frequency. Consider a bond order of 1. We can have a carbon-carbon bond, carbon-oxygen, or carbon-nitrogen single bonds with frequencies in the range of 1300 to 800 reciprocal centimeters. Using the same atoms, but with a bond order of 2, a carbon-carbon double bond, carbon-oxygen double bond, or carbon-nitrogen double bond, they will vibrate much higher, at around 1900 to 1500 reciprocal centimeters. Triple bonds, which are stronger than both double and single bonds, vibrate at even higher frequencies. roughly 2,300 to 2,000 reciprocal centimeters. Thus, we can conclude that stronger bonds require more force to compress or stretch, which means that they will also vibrate faster than weaker bonds. Thus, frequency increases as bond strength increases. A third factor is the masses of the atoms. If we consider the CH versus C deuterium stretch, we see that the CH stretch is much more energetic than C deuterium. Hydrogen is a small atom and can vibrate much faster than larger atoms. We see this hold true for other atoms bound to hydrogen as well. Oxygen-hydrogen, nitrogen-hydrogen, and carbon-hydrogen bonds have high vibrational frequencies. Thus, heavier atoms vibrate more slowly than lighter atoms, so frequency increases as weight decreases. The final parameter is electronegativity. While electronegativity does not affect frequency, it does affect the intensity of the peak. This is because bond polarity affects absorption intensity. For example, a CC single and double bonds are either weak or moderate intensity, while CO single and double bonds are quite strong. This is because as infrared light causes stretching vibrations, bond dipoles will actually change. If a carbon-oxygen double bond lengthens, the bond dipole will be stronger. This increases the intensity of the IR band. Finally, we need to discuss where to find specific bands for functional groups in an IR spectra, and develop a strategy for interpreting such data. We can divide the IR spectrum into 4 regions, roughly 4,000 to 2,800, 2,800 to 1,900, 1,900 to 1,200, and 1,200 to 400 reciprocal centimeters. The first region, above 2,800, is characteristic of XH bonds, or bonds to hydrogen. Triple bonds come at slightly lower frequency, followed by double bonds and finally single bonds. This final region can be very complex and there are often peaks that overlap, and another name for this region is the fingerprint region. In the XH region, we have carbon-hydrogen, nitrogen-hydrogen, and oxygen-hydrogen bonds at the frequencies shown. These stretches are correlated to the energies of the respective bonds. Thus, the OH bond has the highest frequency since it is the strongest bond. One important feature of this region is that alcohols and carboxylic acids can be easily detected because hydrogen bonding causes band broadening. Extensive hydrogen bonding will cause the width of the OH band to increase. What was roughly 100 reciprocal centimeters in width is now as much as 600 reciprocal centimeters in width. The triple bond region is home to the alkynes at around 2,200 to 2,100 and the nitriles, which are slightly higher. The difference between these two is that a strong dipole exists for nitriles due to the electronegativity of nitrogen. This causes strong bands for nitriles but weak or moderate bands for alkynes. The double bond region is complex and many types of double bonds exist, such as carbon-oxygen, carbon-carbon, nitrogen-oxygen, and carbon-nitrogen. What is most informative is the C double bond O, also known as the carbonyl functional group. The carbonyl is common to many types of functional groups, and their vibrational frequencies come at specific regions of the spectrum, as shown below. Finally, the CX region is home to single bond vibrations. The problem with this region is its overall complexity. There are so many single bonds in a molecule that this region of the IR spectrum is often difficult to interpret. However, just like a fingerprint is unique to each person, the fingerprint region of the IR is unique to each molecule.